Double faults. This post explores the double fault exception in detail, which occurs when the CPU fails to invoke an exception handler. By handling this exception, we avoid fatal triple faults that cause the system reset. To prevent triple faults in all cases, we also set up an interrupt stack table to catch double faults on a separate kernel stack. What is a double fault? In simplified terms, a double fault is a special exception that occurs when a CPU fails to invoke an exception handler. For example, it occurs when a page fault is triggered, but there's no page fault handler registered in the IDT. So it's kind of similar to catch-all blocks in programming languages with exceptions. A double fault behaves like a normal exception. It has the vector number 8, and we can define a normal handler function for it in the IDT. It's really important to provide a double fault handler, because if a double fault is unhandled, a fatal triple fault occurs. Triple faults can't be caught, and most hardware reacts with a system reset. Triggering a double fault. Let's provoke a double fault by triggering an exception for that we didn't define a handler function. For which we didn't define a handler function? All right, so in main, we're going to create an exception here. We're clean, right? Yep. So we're gonna, after the init, where's the init? There's the init. Oh, I guess we're getting rid of this. Trigger a page fault, unsafe. Like this, OX dead beef as star.64 equals 42. So this is going to do, does that need to be there? Oh, U64. Yeah, that semicolon doesn't need to be there. So this is just writing to some random piece of memory that might not be paged in. Probably not paged in. We use unsafe to write to the invalid address dead beef. The virtual address is not mapped to a physical address in the page tables, so a page fault occurs. We haven't registered a page fault handler in our IDT, so a double fault occurs. When we start our kernel now, we see that it enters an endless boot loop. The reason for the boot loop is the following. The CPU tries to write to dead beef, OX dead beef, which causes a page fault. The CPU looks at the corresponding entry in the IDT and sees that no handler function is specified, thus it can't call the page fault handler, and a double fault occurs. The CPU looks at the IDT entry of the double fault handler, but this entry does not specify a handler function either, thus a triple fault occurs. A triple fault is fatal. QEMU reacts to it like most real hardware and issues a system reset. I don't know if I want to run it because I don't know if it's just going to keep rerunning, but I'm going to see. Boom, 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 boom. So it keeps rebooting and resetting. We see the hello world. All right, so hopefully, yes. Okay, good, I can kill it. So in order to prevent this triple fault, we need to either provide a handler function for page faults or a double fault handler. We want to avoid triple faults in all cases, so let's start with a double fault handler that is invoked for all unhandled exception types. A double fault is a normal exception with an error code, so we can specify a help handler function similar to our breakpoint handler. Okay, so in lazy static, we'll add an IDT, double fault, set handler function, double fault handler. And then we have to write it. This takes a stack frame and an error code, and it never returns. Panic. Okay. Nice to print out the error code too, why not? I guess we're not doing that. Our handler prints a short error message and dumps the exception stack frame. The error code of the double fault handler is always 0. Okay, so there's no reason to print it. One difference to the breakpoint handler is that the double fault handler is diverging. The reason is that the x86-64 architecture does not permit returning from a double fault exception. So what are you supposed to do then? When we start our kernel now, we should see that the double fault handler is invoked. Got to spell interrupt correctly. There we go, cargo run. Okay, exception double fault. So now this is the interrupt stack frame for the double fault. And we can even see the line number where we panicked. It worked. Here's what happens this time. The CPU tries to write dead beef, which causes a page fault. Like before, the CPU looks at the corresponding entry in the IDT and sees that no handler function is defined, thus a double fault occurs. The CPU jumps to the now present double fault handler. The triple fault and the boot loop no longer occurs since the CPU can now call the double fault handler. That was quite straightforward, so why do we need a whole post for this topic? Well, we're now able to catch most double faults, but there are some cases where our current approach doesn't suffice. Before we look at the special cases, we need to know the exact causes of double faults. Above, we used a pretty vague definition. Double fault is a special exception that occurs when CPU fails to invoke an exception handler. What does fails to invoke mean exactly? The handler is not present, the handler is swapped out, and what happens if the handler causes exceptions itself? For example, what happens if 1. A breakpoint exception occurs, but the corresponding handler function is swapped out. 2. A page fault occurs, but the page fault handler is swapped out. 3. A divide by zero handler causes a breakpoint exception, but the breakpoint handler is swapped out. 4. Our kernel overflows its stack and the guard page is hit. Fortunately, the AMD 64 manual has an exact definition. According to it, a double fault exception can occur when an second exception occurs during the handling of a prior first exception handler. The can is important. Only very specific combinations of exceptions lead to a double fault. These combinations are, so any one of these 5, and then any one of these 4 can happen while we're in one of those 5. Or the first exception is just this one page fault, and then a second page fault occurs, or any one of these other 4 occur. So, for example, a divide by zero fault followed by a page fault is fine. Divide by zero followed by a page fault, we don't mind. It's not a double fault. Page fault handler is invoked, but the divide by zero fault followed by a general protection fault leads to a double fault. With the help of this table, we can answer the first 3 of the above questions. If a breakpoint exception occurs and the corresponding handler function is swapped out, a page fault occurs and the page fault handler is invoked. If a page fault occurs and the page fault handler is swapped out, a double fault occurs and the double fault handler is invoked. If a divide by zero handler causes a breakpoint exception, the CPU tries to invoke the breakpoint handler. If the breakpoint handler is swapped out, a page fault occurs and the page fault handler is invoked. Okay. In fact, even the case of an exception without a handler function in the IDT follows this scheme. When the exception occurs, the CPU tries to read the corresponding IDT entry. Since the entry is 0, which is not a valid IDT entry, a general protection fault occurs. We did not define a handler function for the general protection fault either, so another general protection fault occurs. According to the table, this leads to a double fault. Okay, that makes sense. Let's look at the fourth question. What happens if our kernel overflows its stack and a guard page is hit? A guard page is a special memory page at the bottom of a stack that makes it possible to detect stack overflows. The page is not mapped to any physical frame, so accessing it causes a page fault instead of silently corrupting other memory. The bootloader sets up a guard page for our kernel stack, so stack overflow causes a page fault. When a page fault occurs, the CPU looks up the page fault handler in the IDT and tries to push the interrupt stack frame onto the stack. However, the current stack pointer still points to the non-present guard page. Thus, a second page fault occurs, which causes a double fault according to the above table. So the CPU tries to call the double fault handler now. However, on double fault, the CPU tries to push the exception stack frame too. The stack pointer still points to the guard page, so a third page fault occurs, which causes a triple fault and a system reboot. So our current double fault handler can't avoid a triple fault in this case. Let's try it ourselves. We can easily provoke a kernel stack overflow by calling a function that recurses endlessly. Alright. Oops. So instead of calling this unsafe dead beef thing, we're going to, ooh, I deleted way too much there. Okay, so we're going to do function stack overflow, which calls stack overflow, and we're just going to call it here stack overflow. It builds. What's the warning? Cannot return without recursing. Oh, that's clever. But it allows me to build it. But that's neat that Rust can actually detect the fact that we don't have a recursion ender. Right? Because recursive functions always have a final step followed by a recursive step. Or the other way around. Alright, so now, yes, now it's in an infinite boot loop because we're overflowing the stack, getting a page fault, which causes the stack to fault, which causes a triple fault, which causes a reset. When we try this code in QEMU, we can see that the system enters a boot loop again. So how can we avoid this problem? We can't omit the pushing of an exception stack frame since the CPU itself does it. So we need to ensure somehow that the stack is always valid when a double fault exception occurs. Fortunately, the x86 architecture has a solution to this problem. The x86 architecture is able to switch to a predefined known good stack when an exception occurs. This switch happens at hardware level so it can be performed before the CPU pushes the exception stack frame. The switching mechanism is implemented as an interrupt stack table. The IST is a table of 7 pointers to known good stacks. In Rust-like pseudocode, it looks like this. For each exception handler, we can choose the stack from the IST through the stack pointers field in the corresponding IDT entry. For example, we could use the first stack in the IST for our double fault handler, then the CPU would automatically switch to the stack whenever a double fault occurs. This switch would happen before anything is pushed, so it would prevent the triple fault. Okay, the IST and the TSS. The IST is part of the old legacy structure called a task state segment, TSS. The TSS is used to hold various information about a task in 32-bit mode and was, for example, used for hardware context switching. Okay. However, hardware context switching is no longer supported in 64-bit mode, and the format of TSS changed completely. On x86 64, the TSS no longer holds any task-specific information at all. Instead, it holds two stack tables. The only common field between the 32-bit, 64-bit TSS is the pointer to the I/O port permissions bitmap. And I guess the rest are just empty. The privilege stack table is used by the CPU when a privilege level changes. For example, if an exception occurs while the CPU is in user mode, privilege level 3, the CPU normally switches to kernel mode, privilege level 0, before invoking the exception handler. In that case, the CPU would switch to the 0th stack in the privilege stack table. We don't have any user mode programs yet, so we ignore this table for now. Let's create a new TSS that contains a separate double fault stack in its interrupt stack table. For that, we need a TSS struct. Fortunately, the x86 64 create already contains a task state segment struct that we can use. We create the TSS in a new GDT module. The name will make sense later. Okay, so should we leave? We want to leave the double fault handler here, but do we want to leave this here? Okay, I guess we don't need to commit these changes yet. So in lib pub mod GDT, and then we're going to create GDT. So this is going to use x86 64 vert adder, and it's also going to use structures TSS task state segment. Okay, and then we're going to use the lazy static. pub const double fault ist index u16 is 0. And then we have our lazy static defining the TSS to be a task state segment. Let TSS is equal to task state segment new. TSS interrupt stack table. Why did we define it as U16 if it's just going to be used as U size? Five times 4K, 20K, static, mute, stack, U8, stack size is equal to 0 stack size. Okay. And then we have let stack start, vert adder, from pointer, unsafe, stack. And then this should be stack start, let stack end, stack start, plus stack size. That makes sense. Stack end. So we're setting the interrupt stack table to the end of the stack after we've calculated the stack start. Okay. And then we just return the TSS there. It builds. Do we need to do this then? Can we just do this? And then pull this out as well? This is building, right? No, it's not. Here's pubmod GDT. All right, let me put this back and figure out why this is not. Oh, okay, it did save it because. Okay, I'm confused because I would have thought I would have seen a compilation error if I put something random in there, and I'm not seeing a compilation error, which means to me that this is not being built. There it is. Maybe I have to reset my language thing or something. Okay. Yeah, we still have the stack overflow thing. Okay. I think we're good. We use lazy static because Rust's const evaluator is not yet powerful enough to do this initialization at compile time. I thought they added some const stuff. We'll have to take a look. Maybe there's a PR to fix it if so. Epic Log says yes, the LSP sometimes works. Oh wait, I still have this thing. I want to try this out again. Here we go. Yeah, the LSP sometimes works out. Yeah, and I don't know how to reset it because obviously when I'm... Oh, let me make that go away. Now it's covering things up. There we go. If I restart LSP, it should... Yeah, it's still broken. Maybe there's a separate one running that I need to kill. I mean, there are some. Maybe if I kill these guys. But I thought Rust Analyzer was invoked by... Oh, now they're all running. Okay, I broke something. Yeah, all right, now I'm going to just have to live with it. All right. We define that the 0th IST entry is a double fault stack. Any other IST index would work too. That's the 0 here. Then we write the top address of the double fault stack to the 0th entry. We write the top address because the stacks on x86 grow downwards, i.e. from high addresses to low addresses. That's what they mean by the stack end thing here. We haven't implemented memory management yet, so we don't have a proper way to allocate a new stack. Instead, we use a static mute array as the stack storage for now. The unsafe is required because the compiler can't guarantee race freedom when mutable stacks are accessed. It's important that this is a static mute and not an immutable static, because otherwise the bootloader would map it to a read-only page. We will replace this with the proper stack allocation in a later post. Then the unsafe will no longer be needed at this place. Note that this double fault stack has no guard page that protects against stack overflow. This means that we should not do anything stack intensive in our double fault handler because a stack overflow might corrupt the memory below the stack. Now that we created a new TSS, we need a way to tell the CPU that it should use it. Unfortunately, this is a bit cumbersome since the TSS uses a segmentation system for historical reasons. Instead of loading the table directly, we need to add a new segment descriptor to the global descriptor table. Then we can load our TSS, invoking the LTR instruction with the respective GDT index. This is the reason why we named our module GDT. All right, the global descriptor table. The global descriptor table is a relic, right? I should take notes and then submit PRs for fixes, because I think this is all on GitHub. That was used for memory segmentation before paging became the de facto standard. It is still needed in 64-bit mode for various things such as kernel user mode configuration or TSS loading. The GDT is a structure that contains the segments of the program. It was used on older architectures to isolate programs from each other before paging became the standard. For more information about segmentation, check out the equally named chapter of the free 3 Easy Pieces book. Equally named chapter? I don't know what that means. When the segmentation is no longer supported in 64-bit mode, the GDT still exists. It's mostly used for two things: switching between the kernel space and user space, and loading a TSS structure. Let's create a static GDT that includes a segment for our TSS static. Okay, so that's down here. We'll create a new lazy static. And that's going to contain static ref GDT. Let not GDT. Create a new one. GDT add entry scriptor kernel code segment. GDT add entry TSS segment TSS GDT. Okay. Oh, we have to pull in descriptor and global descriptor table. So should I just pull it in here? Structure is GDT. And then global descriptor table and descriptor. Descriptor. Okay. I'm sure there's an LSP hotkey to combine and clean up all that, but I don't know it. Loading the GDT. To load our GDT, we create a new GDT init function that we can call from our init function. So let's put that right here at the top. Pub fun init gdt.load ad. And then in our lib, and this is in our init here, we say GDT init like that. Now it's going to fail, right? Nope. Now it builds. That's good. So we have to actually call a function in it for LSP to start seeing it. And we still have the Stack Overflow error. That's fine. Now our GDT is loaded since the start function calls init, but we still see the boot loop on Stack Overflow. Okay, let me just check here in main. We call BlogOS init, which calls the init we just did. So this cargo run will still boot loop. Okay. The final steps. The problem is that the GDT segments are not yet active because the segment and TSS registers still contain the values from the old GDT. We also need to modify the double fault IDT entry so that it uses the new stack. In summary, we need to do the following. 1. Reload the code segment register. We changed our GDT, so we should reload CS, the code segment register. This is required since the old segment selector could point to a different GDT descriptor now. Load the TSS. We loaded a GDT that contains a TSS selector, but we still need to tell the CPU that it should use that TSS. And 3, update the IDT entry. As soon as our TSS is loaded, the CPU has access to a valid interrupt stack table. Then we can tell the CPU that it should use our new double fault stack by modifying our double fault IDT entry. For the first 2 steps, we need access to the code selector and TSS selector variables in our GDT init function. We can achieve this by making them part of the static through a new selectors struct. Segment selector. Okay. So we have, oh, I see. Now we're going to say let code selector equals this, and let TSS selector equal that. Okay, and then we're going to return 3 things, so GDT, or 2 things, sorry. Selectors, code selector, and TSS selector. Like this, and that means we're going to change this global descriptor table to be a tuple that contains the selectors as well. We're then going to create a selectors struct, which contains those 2, code selector and TSS selector. All right, so we still have an issue here because now we have to do a .0 load. Okay. Now we can use the selectors to reload the CS segment register and load our new TSS. Okay. So I'll change that and say use x86 64 instructions tables load TSS. And we're going to change this here to segmentation, CS, and segment. Okay, we'll do the load, and then we have a couple of unsafes statements. CS setreg gdt.1.code selector and load TSS gdt.1.tss selector. Wow. We reload the code segment register using setcs somewhere. Wait, this says set reg, and then this says set CS. Is this a typo? This is definitely a typo. Segreg. This should be set. Let's take a look at the docs. There is a CS set reg. Why don't I see that function over here? A set reg and a get reg. So there is no set CS. There is. Oh, it's an alias for set reg. Okay, so that must have been the old way. So this is a type. This needs to be updated to match the current crate. Okay. The functions are marked unsafe, so we need an unsafe block to invoke them. The reason is that it might be possible to break memory safety by loading invalid selectors. Now that we've loaded a valid TSS and interrupt stack table, we can set the stack index for our double fault handler in the IDT. So we go down to the IDT, which is in the interrupts thing here. We set the breakpoint handler, and then in an unsafe block, we set our double fault handler. Oh, and then it returns set stack. It returns something we can call set stack index on GDT double fault IST index. And we're going to need to import use create GDT. And I messed this up. Oh, because I forgot to close my unsafe block. Like that. That works. Oh. Instructions. And then TSS selector. There we go. And then we still have 2 warnings because of the infinite loop. Okay. The set stack index method is unsafe because the caller must ensure that the used index is valid and not already used for another exception. That's it. Now the CPU should switch to the double fault stack whenever a double fault occurs. Thus we are able to catch all double faults, including kernel stack overflows. Okay, let's watch that. Boom, and we caught it. How about that? All that work. From now on, we should never see a triple fault again. To ensure that we don't accidentally break the above, we should add a test for this. A stack overflow test. To test our new GDT module, okay, let's take this code out of main. Right, we don't need any of that. And we can commit these. Epic Blog says, that's pretty neat. I agree. This is a lot of fun, this particular series I'm doing. Git status, git add source GDT, git commit, handling double faults in a separate stack segment. Okay. To test our new GDT module and ensure that the double fault handler is correctly called on a Stack Overflow, we can add an integration test. The idea is to provoke a double fault in the test function and verify that the double fault handler is called. Let's start with a minimal skeleton. So we're going to actually create a inside tests Stack Overflow. So this is not a unit test, this is an integration test. So we have the no standard and the no main. This is similar to our other. So we have 3 tests in here, right? Or 2 other ones. We have the basic boot and should panic. So we're adding a new one, Stack Overflow. So we have no mangle. Unimplemented, and then we have a panic handler. Okay, so this is a skeleton of a test, right? So I think this is going to be like for any integration test we want, we're going to want this kind of a setup. So it'd be nice to be able to have this as a test skeleton. I'll call it .text so we don't try to build it. Okay. The reason is we can't continue. Okay, right. Like our panic handler test, this test will run without a test harness. The reason is that we can't continue execution after a double fault, so more than one test doesn't make sense. To disable the test harness for the test, we can add the following to our cargo.toml. Oh, right. We had to do that for the other one as well. All right, we did it for our should panic. And I guess we just need to stack overflow as well. Okay, very good. All right, so now cargo test stack overflow should compile successfully. The test fails, of course, since the unimplemented macro panics. Let's see what it does. Test stack overflow. Do I have to put the -- test on that, or can I just put the name? And panicked it not implemented. I guess I'm not sure what it tried to run here, but clearly I do need to add this -- test. All right. Implementing start. The implementation of the start function looks like this. Tests stack overflow. There we go. So starts with serial print, bang, stack overflow, tab. BlogOS GDT init test IDT stack overflow, and then panic execution continued after stack overflow. And then we have a function, allow unconditional recursion. New 0 read. Prevent tail recursion optimizations. Okay. You'd think that this would give the clue. All right. We call our GDT init function to initialize the new GDT. Instead of calling our interrupts init IDT function, we call an init test IDT function that will be explained in a moment. The reason is that we want to register a custom double fault handler that doesn't exit QEMU instead of panicking. The stack overflow function is almost identical to the function in our main.rs. The only difference is that we do an additional volatile read at the end of the function using the volatile type to prevent the compiler optimization called tail call elimination. So, we don't use it because we did the whole path there. Okay. Thus, no additional stack frame is created for the function call, so the stack usage does remain constant. Oh, yeah, that's for the tail recursion. Okay. In our case, however, we want the stack overflow. We want that the stack overflow happens. We want the stack overflow to happen. So we add a dummy volatile read statement at the end of the function, which the compiler is not allowed to remove. Thus, the function is no longer tail recursive, and the transformation into a loop is prevented. We also add the allow unconditional recursion attribute to silence the compiler warning that the function recurses endlessly. As noted above, the test needs its own IDT with a custom double fault handler. The implementation looks like this. So we're going to add our own here. Use lazy static. And use x86-64. Interrupt descriptor table. Let me do IDT is equal to this thing, new, unsafe, IDT double fault. So we have the set handler, function test double fault handler, and a set stack index is equal to BlogOS GDT double fault ist index. And then we return IDT, and then we're done with that. And then here's init test IDT. I don't think it has to be pub, but it doesn't hurt to be pub. Okay, the implementation is very similar to our normal IDT in interrupts.rs. Like the normal IDT, we set a stack index into the IST for the double fault handler in order to switch it to a separate stack. The init test IDT function loads the IDT on the CPU through the load method. The only missing piece is our double fault handler. It looks like this. Okay, so now we're going to add a use BlogOS exit QEMU exit code serial println. And then here we're going to add IDT interrupt stack frame. Oops. Fix the missing colon too. And then we have our interrupt. So this panic, that stack overflow, there's our start. Right here, I guess. Extern, x86, interrupt, function, test, double, fault, handler. Stack frame, which we were ignoring, interrupt stack frame, error code, which we also ignore, U64, and this diverges, and then we have serial print when okay. Exit QEMU exit code success, and then infinite loop. There we go. When the double fault handler is called, we exit QEMU with a success error exit code, which marks the test as passed. Since integration tests are completely separate executables, we need to set this. I forgot that part. No. There we go. I guess we could put it last time. Now we can run our test through cargo test stack overflow or cargo test to run all the tests. As expected, we see stack overflow OK output on the console. Try to comment out the set stack index line. It should cause the test to fail. Okay. Cargo test stack overflow. Of course it doesn't work if I typo it. Oh, okay. But we need both serial print and serial println. Okay, let's try again. There it is. And then if we want to comment out set stack index, that should show that the test fails without it. Right. If I just put a semicolon here. And now it's an unnecessary unsafe block. And we have error test failed. Doesn't say what failed, but we did have a failure. So let's put this back. Overly long loop. Hello, Mouse X. Good to see you. So now we should be able to run all the tests, and they should all pass. It's hard to read the output, and you have to kind of grep using igrep for all the OKs, but they're all there. Okay, so now we're going to say git commit -m added integration test for stack overflow. Look at that, and we're done.